Everyone, welcome to Steward Observatory on this beautiful February evening in Tucson, Arizona. We also welcome you, those of you watching our podcast online at www.as.arizona.edu. Before we begin with tonight's proceedings, I would like to pay tribute to the fact that Steward Observatory lost a very good friend last week. Father George Coyne, Society of Jesus. Father Coyne was a PhD astronomer as well as a Jesuit priest. He was made director of the Vatican Observatory by His Holiness Pope John Paul I. Now, as you know, John Paul I was only Pope for 3 weeks. And it's one of the few things he did was appoint Father Coyne as director of the Vatican Observatory. And he was director from 1978 until 2006. But he also served on the faculty here, both at Steward Observatory and at Lunar and Planetary Laboratory. He was also the interim director of Steward Observatory from 1978 to 1980. And he was responsible basically for moving the observational part of the Vatican Observatory to Tucson, with the culmination of the Vatican Advanced Technology Telescope on Mount Graham. And of course, we have Jesuits running around this building, thanks to George. He passed away last Tuesday in hospital in Syracuse, New York. After he retired from the Vatican Observatory, he was teaching high school in upstate New York at a Jesuit high school. And he passed away from bladder cancer at age 87. So, we say a fond farewell to Father George. Now, tonight is our only public evening lecture for the month of February. Our next lecture, 2 weeks from tonight, will be on March the 2nd. It'll be March already, 2 weeks from today, where Katie Greer will actually give the talk she was supposed to give in November about supermassive black holes, but was too ill to do it. If there are any students in the audience, I am the person who will validate your assignments right up here at the conclusion of tonight's lecture. And the telescope, it's a clear night. The telescope will be open for your public viewing pleasure. It's the white building right next door. So, we've had a lot of anniversaries to celebrate recently here at Steward Observatory, and it turns out that it's been 50 years ago, early 1970, that radio astronomy started here in southern Arizona. And so Professor Yancy Shirley wanted to give a talk about that subject. Yancy is one of our alumni. He received his Bachelor of Science degree in astronomy from the University of Arizona. Then he received his PhD in astronomy from the University of Texas, which is in Austin. After that, he won a Jansky Fellowship and was a Jansky Fellow at the VLA, the Very Large Array in Socorro, New Mexico, at the National Radio Astronomy Observatory. And then he came here. And he's been on our faculty since
2008.
Since 2008, so that's 12 years he's been on the faculty. He's a professor here at the University of Arizona, and he is going to talk to you about the celebration of 50 years of molecular cloud science, which also coincides with 50 years of radio astronomy being performed in southern Arizona. Yancy.
So thank you very much, Tom. Just make sure I'm on.
Start talking.
Okay. All right, we'll test out. We didn't test out the mic earlier, so maybe a little higher. Is that right? Yeah, okay, there we go. Perfect. Okay, can everyone hear me? Yeah, how are you? A little louder? I can be louder. I can project, so theater is not a problem for me. This is what happens when you're a professor for 12 years. You learn how to project in a large lecture hall. So, well, welcome everyone this evening, and I wanted to talk to you about a topic that maybe many of you may not have heard of, and that is the topic of molecular cloud science. And it's a topic that's near and dear to my heart because it's a research area that I've been working in for the last, really now, 20 years of my life since I was a graduate student at the University of Texas. We're coming up on the celebration of a 50th anniversary that's happening this April that happened on Kitt Peak. And so what I'm going to be talking about today is a little bit of the history behind that event in all the great science that we've been doing over the last 50 years since we've discovered molecular clouds. So what I'm going to do today is sort of step you through a little bit of our understanding of what these objects are. So if you look at this beautiful image that we have here, and I think Tom's going to help with the lights a little bit tonight, because there's some, I tried to pick out some really stunning high-resolution images, hopefully to show, except for that one bad light there. There we go. All right. Perfect. So this is the Milky Way. So how many of you have gone out, especially on a summertime night, out in the desert here in Arizona and seen the Milky Way? All right. So almost everyone. Now, if you were alive over 100 years ago, before the modern electrical conveniences that we have now, this would have been a common sight to you, and you would have been very familiar with these dark, dusty regions in the Milky Way. Matter of fact, they were so familiar, for instance, to Aboriginal astronomers or indigenous astronomers in Australia, that they actually made a constellation out of these. So it's called the Emu in the sky. If you go over here to, this is in the southern hemisphere, this dark cloud is called the coal sack. This is the head, and this is the little beak of the emu. Here's the neck, going down to a body, down to the feet, right down there. And all this is visible from Australia, this entire part of the plane of the Milky Way galaxy. And so they actually made a constellation out of the dark clouds that you see in the Milky Way galaxy. Now, for a long time, people really didn't understand what these dark clouds were. So even as late as the late 18th century, William Herschel wrote in one of his notes that when looking at one of these regions with a telescope, surely there is a hole in the heavens. So the prevailing scientific wisdom of the late 18th century and all through the 19th century was that these were voids, places where there were no stars, empty space, as you would have it. They didn't really understand the concept of obscuring clouds of material until really the beginning of the 20th century. And it was this particular astronomer right up here, this is E E Barnard, he's an American astronomer, that was using photographic plates and sort of the best technology of the time to start making images of these vacancies, these places where there are no stars. And it really wasn't until E E Barnard's paper in 1907, in this particular image, which is one of these vacancies and nebula, the nebula is this little fuzzy patch here that's in the central part of Taurus, that led E E Barnard to realize that these were really obscuring bodies, obscuring clouds of material. So here's the quote from the paper. I've been slow in accepting the idea of an obscuring body to account for these vacancies. Yet this particular case almost forces the idea upon one as fact. There are portions of this apparent vacancy that are clearly darker than the adjacent sky. So E E Barnard was the first to really truly realize that there were these large clouds of dusty, gritty material in space that were clouds of actual stuff that were obscuring the background starlight. Now, this was a hard observation to make. This was the state-of-the-art photographic plate in 1907, and it's kind of hard to see where the dark cloud is. All E E Barnard needed was a digital DSLR camera, and he would have seen this. And it would have been a very easy observation to make because clearly this is an obscuring, dusty cloud. So what's causing this? Well, there's solid particles in space. There's grit. They're very fine. They're much finer than the typical dust that you find in your house. And astronomers call this gritty solid material dust. All right? And so here is actually a microscopic view of a dust particle. This is actually captured by a U-2 aircraft flying at high altitude in the stratosphere of the Earth. It sticks out a little piece of aerogel, and it can pick up solid particles in the Earth's upper atmosphere. You can take them to a laboratory, and you can test their compositional makeup. And we know that this particular particle formed outside of our solar system. It has the particular elemental composition that tells us that. So this is an example of one of the types of dust grains that you might find in this dusty cloud. It's about a micron in size. They're really, really tiny. But they're just about the right size that they do a really, really efficient job of absorbing and scattering short wavelength light. So the kind of light that our eyes can see at visible wavelengths, all the gritty stuff that's in this cloud is absorbing and scattering that short wavelength radiation, and that's why this appears as an opaque cloud to us at visible wavelengths. So this was really the first discovery and the first recognition by E E Barnard that there were these molecular clouds. So what do we know today? Molecular clouds are important to study in our Milky Way galaxy and other galaxies because they are the birthplaces of stars and planets. This dusty, gritty material that you see here is the raw material at which stars and planets are forming today. in our Milky Way galaxy. And this beautiful image of a molecular cloud in Monoceros by Adam Bloch shows this actually happening. Do you see this red region in here and all these sort of reddish or yellowish looking stars? These are young stars that have just been born recently and are emerging out of their parent cloud. So if we want to understand the process of how stars and planets, and especially if we want to understand where our solar system came from, we need to study these molecular dusty clouds if we want to study these particular regions and how this physics happens. So some of the most famous images you've probably seen in astronomy are of molecular clouds. So this image right here, which is probably one of the most iconic Hubble Space Telescope images, these are the pillars in the middle of M16, the Eagle Nebula. This dusty stuff you see here is a molecular cloud. It's part of a much larger molecular cloud that's being eaten away from a very young, hot, massive star that just formed, and that's what's illuminating the tips you see of this particular pillars in this molecular cloud. How about this one? The Orion Nebula. This is something you can go look at through the telescope, the 20-inch telescope after the talk tonight, because it will be up and easily visible through the telescope. But this here is a very, very beautiful, deep astrophoto of the Orion Nebula. What makes it spectacular, though, is all this material that's around here. This surrounding dusty material is the molecular cloud. And the young stars down here, the cluster that's forming, that's lighting this whole region up, has emerged from this much larger molecular cloud. How about this one? This one I really like. Some of these have good names to them because they actually look like the shapes they're supposed to be. This right here is called the Horsehead Nebula. It's also in Orion. It's just off the left belt star of Orion, just below it. It's also called Barnard 33 because guess who? E E Barnard cataloged this as part of his photographic plates. This was one of the regions that he actually looked at. So here's the Horsehead Nebula. Here's another one that I really like. This one, if you ever see astrophotos taken of the Milky Way, especially in the direction of Sagittarius and Ophiuchus, you'll see this very distinct feature just above the galactic plane. It's called the Pipe Nebula. So this is the stem of the pipe, this part of the dark cloud. This is the bowl of the pipe, and there's even some smoke coming out of the pipe you can see there. For the younger college students in the audience, let's just call it a bong, and we're all good. Okay, so I'll be showing you some results later that have the Pipe Nebula in it as well. Well, what really makes these things interesting is that these are the places where you want to go study how stars and planets form. But there's a fundamental problem with trying to study them at optical wavelengths. So this is an example of one of these dark clouds. This is actually a little small one. It's only about a little over a light year across. It's relatively nearby to us, only about 300 parsecs away. And it's kind of sitting all out in its own little lonesome here in front of this bright star field. This is called Barnard 68. And the problem is if you want to see what's going on down inside of this cloud, it is completely opaque. You cannot see inside of this cloud because there's so much dust in this dusty molecular cloud that it's obscuring what might be happening in the middle part of this cloud. And you might say, okay, well, this is optical wavelengths, and if you have very good eyesight, you might notice at the very edge of this cloud, some of the stars appear red, so it looks like red light is getting through this dusty material a little easier than maybe blue light is. Well, what if we go to even longer wavelengths, like into the infrared? Well, it turns out for the vast majority of molecular clouds, that doesn't help you either. This is an image from the Spitzer Space Telescope. And I think you all heard a talk 3 weeks ago about the many great discoveries of the Spitzer Space Telescope. So this is an infrared image. The three colors you see here are false colors. They correspond to wavelengths that are about 4 times longer, about 8 times longer, 16 times longer, and about 50 times longer than yellow light that our eyes are sensitive to. So these are infrared wavelengths. And what you will notice is that you see dark, obscuring clouds of material here, even in the infrared. Some of these clouds have so much material, so much grit in there, that even if we go to longer infrared wavelengths, we still cannot see into them. So we need another way of probing these particular clouds. And so that's what the discovery that I'm talking about tonight is really all about. So you notice I've been using a word over and over when I've been talking about these dust clouds. I've been using the word molecular cloud. Well, that's because the major component that these clouds are made out of is molecules. It's actually molecules that exist in space that comprise the gas that's in these clouds. And this is a fact that was not understood until the discovery that I'm talking about tonight in 1970, that happened 50 years ago. So let me try to lay out a little bit of the history of how this came about. So people had never detected molecules in space until 1937. This was actually the first detection of a molecule. It was a simple little diatomic molecule. It was a carbon and a hydrogen atom bonded together, the CH molecule. It's a highly reactive molecule. It's something that would exist in our Earth's atmosphere for any length of time. It would react immediately and turn into something else. So in the near vacuum of space, this is a molecule that can exist for a little bit longer before it collides with something and chemically reacts. Now, when this discovery was made, this was an enormous surprise. It was a discovery that was made at optical wavelengths, and what happened was there was a background star, and the optical wavelength light passed through a very diffuse part of a molecular cloud, and the CH molecules along that line of sight absorbed out at very particular wavelengths the light from that background star, and that's how they are able to identify this particular molecule. At this point in the late 1930s, astronomers didn't think that molecules could exist in space. There's a fundamental problem with trying to get a molecule to sit out there in space for a long period of time. The problem is UV radiation, okay? And it's sort of one of the main things that our ozone layer does here on the Earth, protects us from UV radiation. Molecules do not like UV radiation. UV photons have enough energy that they can break the bonds and break molecules apart back into their atomic constituents. So people thought that from just the general starlight, from all the stars in the Milky Way galaxy, that the background UV radiation should break apart molecules, and you shouldn't have molecules existing for any measurable amount of time. So this was a real discovery and a real eye-opener. Okay, somehow molecules can exist, reach appreciable abundances, so that we can actually observe them. Now, a long period of time goes before the real revolution starts, which really started in 1968. And what happened in the intervening years was World War II. A lot of radar engineers worked on technology for radar during the war, especially for the Allies. And after the war, some of those electrical engineers became the first generation of radio astronomers. So through the early 1950s and 1960s, you had a lot of very quick development of radio astronomy. And then the first real breakthrough came in 1968. It came from the group at Berkeley. This is Charlie Towns. He's a Nobel Prize winner. He won the Nobel Prize actually for the invention of the maser, which is basically a laser that works at microwave wavelengths. And so he did that discovery work at Columbia and then moved to Berkeley, where he started a research group to try to study molecules. And he made several predictions here in the late 50s and early 60s about different kinds of molecules that might be detected in space. The vast majority of the astronomical community ignored Charlie Towns and his colleagues. They thought this was a complete waste of time. Molecules, this little CH is a weird, odd case. There's not vast reservoirs of molecules in space. The UV radiation should destroy them all. But Charlie kept at it, and in 1968, using telescopes in Northern California, they were able to detect emission, actually, from a 4-atom molecule. This is ammonia, nitrogen with 3 hydrogens, and they could see transitions from ammonia. And this was the breakthrough that was needed, okay, in 1968. Simultaneous to this, a radio telescope was being built that would work at the wavelengths where you can see these molecules radiating in the radio part of the spectrum. And so the telescope was what was originally called the 36-foot telescope, and it was built on the southwest ridge of Kitt Peak by the National Radio Astronomy Observatory, so the National Observatory for Radio Astronomers. It saw first light actually in October of 1967, so I guess you can say we've been technically doing radio astronomy here in southern Arizona for about 53 years in general, but it was 1970 where the real breakthrough happened. So what happened in 1970 that opened things up? It was detection of this particular molecule right here, carbon monoxide, CO. This discovery in April of 1970 provided us with the observations that were the real tracer of molecular clouds. So let me explain now a little bit about this discovery and why this is such a good tracer of molecular clouds, why this particular anniversary is so important for an entire field of astrophysics. The discovery is due to this person right here. This is Bob Wilson. He's an American astronomer, grew up in Houston, went to Caltech for his PhD, and then went to work at Bell Labs. Now again, for all the younger members of the audience, don't know what Bell Labs is. Bell Telephone Company used to be a monopoly, and a little bit like Google is today, they had a lot of disposable income to spend on research projects and had gigantic laboratories and hired a lot of scientists, including radio astronomers. Why did they hire radio astronomers? Because they were a telephone company and they were interested in communications problems. Well, it turns out that Bob Wilson started working in the early 1960s at Bell Labs. Bob Wilson and his colleague Arno Penzias worked on a 20-foot horn antenna in New Jersey and made quite possibly one of the most important discoveries of the 20th century in astrophysics. Does anybody happen to know what that is, what they discovered? Cosmic microwave background. This is the same person, Bob Wilson. This person needs to be better known, I think, especially among the public in terms of his discoveries. So the Bell Labs group continued working on instrumentation, and it turns out in 1970, the Bell Labs research group in New Jersey had the best detectors at the wavelength that carbon monoxide would emit at. It's a wavelength at about 3 millimeters in terms of wavelength in the radio part of the spectrum. So Bob Wilson came out with two other colleagues, Ken Jeffords and Sandy Weinreb, and they spent a whole week here in April working up here at the prime focus of the 36-foot radio dish on top of Kip Peak, trying to install and get their receiver to work. And they had all kinds of problems, all kinds of electronic problems. They couldn't get the receiver to even turn on properly. They couldn't register any signal. And so it took this entire week. And Sandy Weinreb had other things that he needed to do, so he left, okay, at the end of the week. And Arno Penzias hadn't even shown up yet. Arno was coming out for the observing run, but for the second part. So on the night between Sandy leaving and Arno showing up, they finally got the receiver to work on this telescope. And they looked at their possible source list, possible targets they could look at, and said, well, what's up right now? Well, the first object that was up, that was easy to observe, was the Orion Nebula. So that's where they decided to go point first. And when they did, they saw this. What's amazing is the signal from carbon monoxide, this is the actual plot from their 1970 paper, was so strong that they actually saw it on the spectrometer in real time. This is really amazing to think about because the electronics at that point was pretty rudimentary compared to what we have now 50 years later on radio telescopes. And so when the operator was actually slewing the telescope over to the Orion Nebula, Bob Wilson was looking at the spectrometer outputs, just random noise, and then all of a sudden this big spike goes up. And he's like, whoa, whoa, wait, what happened? And so he asked the operator, can you just move the telescope back off the Orion Nebula? Let's make sure everything's working okay. And then the signal went back down and went away. And that was the discovery of carbon monoxide. It was so easy to do. All it required was somebody to go look for it in the first place. And it took the dedication to build the detector and the perseverance to believe that you could actually detect these molecules in space. So this paper that came out in June of 1970 revolutionized astronomy in terms of the study of these particular clouds. We realized that these molecular clouds could now be traced. We now had a tracer that could peer inside the clouds and we could study their interiors. So why does this work? Why does CO work? Well, it turns out that every molecule has a unique fingerprint, essentially, a unique set of frequencies or wavelengths that that molecule will emit at. So here's an example of the spectrum of carbon monoxide. So down here on the x-axis is frequency. Every little spike you see here is a spectral line of carbon monoxide. So it has one at about 115 gigahertz, another one at 230, another one at 345, another at 460. You'll notice the carbon monoxide, being a relatively simple molecule, has this very regular pattern in the spacing of the frequencies of the spectral lines. So you can tune up your radio telescope to this frequency, which, by the way, is about 1,000 times higher than the high M of FM on your radio dial. And you can go look for carbon monoxide in space. That's what Bob Wilson did in 1970. What about some of the other molecules? What about this ammonia molecule that was detected 2 years prior? Well, ammonia, it's got 4 atoms. It can rotate in different ways, so it's a little more complicated. So you notice that it still has a very regularly spaced spectrum, but if you look closely, you'll notice that there's some overlapping lines here. It's a little more complicated in terms of its spectrum. This is in general true. The more complicated your molecule gets, the more complicated its spectrum will be. Here's one that's an organic molecule. This is acetaldehyde. By the way, when you drink ethanol, this is what your liver turns the ethanol into that gives you a hangover. This is why this is an important molecule. It's also, as I'll show you at the very end, it's also well detected in space. But look at its spectrum. Look how many different spectral lines it has. It emits at all these different frequencies or all these different wavelengths throughout the radio part of the spectrum. So it's quite complicated, but we know what all these are very precisely, and we can tune up to them and we can observe acetaldehyde or ammonia or carbon monoxide or water. We can see all these molecules in space by tuning up the radio telescope to the unique frequencies at which they emit. Now, why carbon monoxide? Why is this such a good tracer? So let's start actually with this, the periodic table of the elements that we have here. Can anybody tell me what is the most abundant element in the universe? You'll find the most number of these atoms. So what is it? Hydrogen, exactly. So the first thing in the upper left, hydrogen. So if you were going to form molecules of hydrogen, the simplest molecule we would make is H2. Two hydrogen atoms bonded together. It turns out that this particular molecule has a major problem. It doesn't radiate in the radio. This is what its radio spectrum looks like. And this is not a mistake. It's completely blank because there are no spectral lines. It doesn't have any frequencies at which it radiates. Nature has been extremely unkind to us. So in these molecular clouds, the most abundant constituent of them, by far, 90% is, by number, is molecular hydrogen in these particular molecular clouds. But we can't see it. We're completely blind to it because it doesn't radiate. It doesn't give off any light. It's just transparent, and we see nothing in those particular clouds. Okay, well, if we can't observe the hydrogen in these clouds, what else can we look at? Well, the next most abundant element in the universe is helium. It's over here on the right-hand side of the periodic table. But remember, this right-hand column are all the inert gases. These are the things that don't like to react with other atoms. So helium does not easily form molecules, and it also does not radiate in these molecular clouds. So the second most abundant constituent, which is about 10% by number of the particles in the cloud, also does not radiate, and we're completely transparent to the helium in these clouds. We can't see it at all. So this is sounding really bad for us. It sounds like we might be out of luck here in order to be able to probe the gas in these molecular clouds. Does anybody know what the next two most abundant atoms are in the universe? You can kind of guess from the molecule I'm talking about. So carbon and oxygen, yes, exactly right. So carbon and oxygen, because stars make these elements by burning hydrogen and helium in their interiors and then spew their guts back out into the interstellar medium, and they put out carbon and oxygen, which can then later form molecules. So CO is actually the simplest molecule that you can form, and luckily for us, carbon monoxide radiates easily in these molecular clouds. It's easy for it to get excited, for it to make light, so that we can observe it. So, in terms of the constituents, we can't see the molecular hydrogen, we can't see the helium, but the next most abundant things, carbon and oxygen, when they get bonded together, we can observe them. They radiate, even down to just a few degrees above absolute zero. Carbon monoxide will still give off light at radio wavelengths. That's that really remarkable capability. But its abundance is 1/14,000th compared to H2. That means for every one carbon monoxide molecule, there are 14,000 molecular hydrogen molecules in these clouds. So this is really a trace component of the molecular clouds, but good for us, it's a good tracer of the molecular clouds. So let me show you just how good this is. So remember the Horsehead Nebula? Over here is an optical image of the Horsehead Nebula. This is taken by the 4-meter actually on Kit Peak, that particular image. Here is an image made with a radio telescope of carbon monoxide glowing in that cloud. So everything you see here that is sort of in a yellow color is the carbon monoxide molecules giving off light within the molecular cloud. So here is a very dusty molecular cloud at optical. You can't see into it. You don't know what's going on. Over here is carbon monoxide glowing all the way throughout the cloud. We can see into the cloud and all the way through the cloud with carbon monoxide. The carbon monoxide is such a good tracer. Notice this little tiny whiff under the nose of the Horsehead. There it is right there, emitting in carbon monoxide. So carbon monoxide really is an excellent tracer of this gas in the cloud. And it was this property of the carbon monoxide, the fact that it's so good at seeing the molecular gas in these clouds, that opened up an entire field of science. We now had an ability to not say that these are just dark, obscuring clouds, but actually use a tracer to go in and study what's inside of these clouds. We could use radio telescopes and the carbon monoxide emission to see basically inside the clouds. Now, the Horsehead Nebula is actually right here. This is a CO emission map of part of Orion. The Horsehead is actually a tiny little part of a much larger molecular cloud. So everything that you see here that's emitting in different colors is from carbon monoxide molecules that are glowing in this much larger molecular cloud. If you had eyes that could see this kind of emission in the radio, and you looked up tonight at the constellation of Orion, here's the belt, there's Betelgeuse, which is looking a little faint these days. Down here's where the Orion Nebula is. All this material that you see here is part of a large, giant molecular cloud where young stars are being born today in the direction of Orion. If you take the CO emission and you add up the total amount of material that it traces in this whole region, there's several 100,000 times the mass of the sun worth of gas in these molecular clouds. These are big structures. And if you really think about it, we were missing some of the largest structures in our Milky Way galaxy until 1970. We didn't even know that they existed, that they were so big, so massive, and contained so much gas, because we didn't have the observations to probe them until that key observation in April of 1970. Well, CO emits in all of these clouds. So do you remember that filament I showed you at the very beginning from E E Barnard? That was the one that he decided that these had to be obscuring clouds of bodies? Here's what it looks like in CO emission, right there. It's actually, the E E Barnard photograph was about this region right here. It's part of a much larger complex that if you look up in Taurus, spread out your hand from thumb to pinky, the whole molecular cloud in Taurus spans greater than that distance up in the sky. Okay, it's much bigger than 10 degrees across from end to end, more like 15 to 20 degrees across the entire molecular cloud. Well, we've used this molecule, and starting in 1970, people started mapping molecular clouds in it. The race was on, and a lot of that fundamental work was done on Kitt Peak at the radio telescope. And so by the time the early 1980s roll around, we had our first maps of the entire galactic plane. So down here's this image that I showed, the very first image of the talk tonight, the optical image of our galactic plane. This is the direction towards the galactic center, so about 28,000 light years, there's a black hole in that particular direction. Here's the head of the EMU there. And up here is the corresponding map of emission in the carbon monoxide molecule. So you'll notice all these little streamers that are up here in Ophiuchus, they have all got plenty of carbon monoxide and they're glowing. This big feature here is called the Aquila Rift that juts way up out of the galactic plane. It's a big, giant molecular cloud that's jutting up, and we can see the CO emission emitting from all that region. So it's from studies like these that we were able to now finally piece together for the first time what the molecular content was of our Milky Way galaxy. So what are some of the properties of a typical molecular cloud when you observe them? Okay? So these molecular clouds have a huge range of sizes and mass. On the smallest end, they maybe have about a sun's worth of mass and are maybe a light year across. On the biggest end, the largest of these clouds in our galaxy span several hundred light years across and contain up to 10 million times the mass of the sun. So these are the largest physical structures in the Milky Way galaxy. And again, we didn't understand that they existed as these large, gassy, massive structures until we were able to detect the carbon monoxide emitting in them and study what's happening inside of them. They're cold. It turns out that most of the gas in these clouds is actually only about 10 to 20 degrees above absolute zero. It's really, really frigid. So that's about minus 450 Fahrenheit in terms of the temperature. It's not a place you'd want to hang out in these particular molecular clouds. They're really low density. If you just take an average place in our Milky Way galaxy, and you take a little volume that's 1 cubic centimeter, so about that big in size, not in a molecular cloud, just in an average place in the Milky Way galaxy, on average you'll find about 1 hydrogen atom per cubic centimeter. By the way, in this room, you'll find something like 10 to the 19 molecules in that same little volume, okay? So space is a really, really good vacuum. Inside these molecular clouds, the average density is more like 100 molecules per cubic centimeter. So they're still really, really close to a good vacuum. They're better than any vacuum we've ever created here in a laboratory on the Earth, but they're about 100 times denser on average than just the average density of the material between the stars. Something else that's really interesting about these clouds, and you've probably sussed it out from some of the images, these are not simple spherical structures. They're complicated. They are very filamentary, very frothy. sort of to use a word from how like hydrodynamics, how fluids flow, these things look turbulent. And sure enough, they are. They're very, very turbulent in their structure. So one of the ways that we can actually study the physics of these clouds is by looking at the spectrum of the CO, by looking at the actual spectral line. So how do we actually do that? So for instance, when we observe CO, all the light is not coming out at exactly one frequency. There's some spread to the light in frequency. So most of it's coming out at this frequency, but there's less of it coming out at these frequencies over here and these frequencies over here. So this is what's called a spectral line. And there's two key pieces of information that we can get from an observation like this by spreading out the light and looking at how much intensity there are at different frequencies. First of all, where the peak of this spectral line is very important. The Doppler shift affects the frequency at which this peak shows up. So for instance, if you have a molecular cloud and it's coming towards all of you, when the CO emits its radiation in that cloud, those wavelengths or those frequencies will get shifted towards you, over to this side, over here. So this whole spectral line will shift to the blue side of the spectrum. If that entire molecular cloud were moving away from you, then this central line would shift to the red part of the spectrum. So by measuring this frequency of where this peaks up, we already know something about how the cloud is moving relative to us. Is it coming towards us? Is it going away from us? How fast is it moving towards us? How fast is it moving away from us? You can make that measurement by measuring this center line. The second measurement that's really important is the width of this particular line, how broad it is across here. How wide a range of frequencies does it cover? So if you think about the actual molecules that are in the cloud, the molecules are all moving around randomly inside this cloud. Some of them are moving towards you, the observer, and some of them are moving away from you. If the cloud is really, really stirred up, and the gas is really moving inside that cloud, it's very turbulent and stirred up, then you're going to have a much wider spread, things that are moving much faster this way or much faster this way, than if everything is very quiet and quiescent and things are just kind of moving around at sort of the typical thermal speeds that you'd expect. So the width of this line tells you something fundamentally about how stirred up the gas is in these particular clouds. So we can use this information. By the way, this is information that you have no chance of ever getting from the optical observations. It's particular information that comes for free by observing the carbon monoxide with a radio telescope. And it tells us how the gas is moving inside these clouds. So let's take our observation of Taurus here. Again, this is the central E E Barnard filament right here. Everything that is color-coded here are different parts of the cloud that are moving at different speeds relative to us. Their CO lines are peaking at different frequencies, and we've measured those, and we've now color-coded them here. Let's zoom in on this particular central filament, because if we do, something really interesting is happening. Okay? So this is the central part of the filament here. It's colored in green. It's at one particular velocity that this object is moving away from us. What you notice is that on one side of the filament, the gas is red-shifted compared to the velocity of this filament. And on the other side of the filament, the gas over here is blue-shifted. It's as if there is a flow of gas coming in onto this central filament. Just by looking at the central velocities of the lines and also their widths, we're able to measure how the gas is moving. This filament is collecting material. Gas is raining down onto it, and we can trace that with the carbon monoxide emission. If you measure how much of this mass that's flowing, there's on the order of about 10 times the mass of the sun for every light year stretch that you have a little distance here of a light year within this filament. And that's over the course of about 1 million years. If you wait 1 million years, about 10 times the mass of the sun will fall into that region in the filament. So if you want to study how stars are forming in this particular region, this piece of information is crucial to understanding how they evolve, because there's fresh material coming in all the time that can feed these young forming protostars in this particular system. Here's another example. This one I really like. This is actually from an astronomer here at the University of Arizona, Shuao Kong, and he made these observations towards a cloud that's about 6,000 light years away in the plane of the Milky Way galaxy. Now what he did is he took the CO line profile, so this thing right here, he cut out all the emission in the middle, and he only looked at the very extremes. He said, let me find the gas in this molecular cloud that's moving really fast towards us or really, really fast away from us. Let me look at these very extreme velocities, and let me make a map of it and see where it shows up. And look at this. Really interesting. You notice a pattern with a lot of these? So here's the central filament. Here's the blue shifted gas. Here's the red shifted gas. Here's another one. It's got blue shifted coming this way and red shifted coming this way. These are jets of high velocity material. From these observations in CO, it was discovered in 1980 that all protostars, young forming solar systems, when they form, they go through a phase where they launch bipolar jets that shoot material out of those solar systems back into the surrounding molecular cloud. And you can see that by studying the carbon monoxide spectrum in these regions. And so what Schwal is doing is he's studying how these things are all aligned with the particular parent filament that they're forming out of. He's been analyzing those structures. So you can see just from this one little observation, just looking at how the frequency of the light spreads out for carbon monoxide emission, there's all kinds of information embedded within those observations that tell us about how stuff is moving within these molecular clouds. When you put it all together and you start to look at these regions, people actually started to realize really early in the 1970s that there was a problem with our understanding of these clouds. So if you actually look across our entire Milky Way, in particular at infrared wavelengths, we know today that stars are forming in our Milky Way galaxy at the rate of about 1 solar mass per year worth of stars is forming in our Milky Way today. That's what our galaxy is cranking out in terms of new stars. Now, by 1974, so only 4 years after the discovery of CO, we had mapped enough molecular clouds in the Milky Way galaxy that people started to get a picture for how massive these things were and how big they really were. Now, if you assume that all the gas in a molecular cloud collapses down as fast as it physically can, and 100% of it goes into stars, you can predict what the star formation rate in the Milky Way should be, given all the molecular gas that we see. So this calculation was done by Ben Zuckerman and Pat Palmer in 1974. Also, my thesis advisor, Neil Evans, was part of this observation when he was a grad student as well, this team. If you do this calculation based on the observations, you would predict a star formation rate in our Milky Way galaxy that is a couple hundred times larger than what we actually observe. So this tells you something right there about how these molecular clouds form stars. They are not 100% efficient. In fact, they have very low efficiency. Only a few percent of the actual material in a giant molecular cloud actually makes it into stars. The rest of it gets blown away, recycled back into the interstellar medium. So this process of star formation is not a very efficient process in our Milky Way galaxy. What helps make this efficiency so low? Feedback. Feedback from the young forming stars that are blowing jets out, the really massive stars that start to ionize and dissociate the molecular cloud. That feedback from those young forming stars can help destroy the very clouds that they're forming out of and make this whole process a very, very inefficient process. Not only that, you need something else besides gravity to hold up this physical process. If gravity was the only thing that was at work, these clouds would just collapse very quickly and they would have a very high efficiency, even with this feedback of forming stars. So you need other things, other effects, like turbulence in the cloud to provide a pressure support that can help hold the clouds up a little bit longer to keep them from collapsing and being so efficient, or even magnetic fields in these particular clouds. So people have been doing simulations now for almost 50 years, trying to study this process. And believe it or not, this is still not a completely solved problem. It's because it's an incredibly difficult physics problem to put all the physics in appropriately to completely model how these clouds collapse. So this is from a simulation by Chris Federath, who's in Australia. So I do Helios Center, right? So let me show you a little bit of a movie here. This is a simulation where what Chris has done is he's simulating a molecular cloud collapsing. This is just pure gravity up here. Right here is gravity with a little bit of turbulence. This is gravity with turbulence and magnetic fields included. And this is everything that he can think of: gravity, turbulence, magnetic fields, and feedback from the forming stars. You can see you get very different answers depending on what kind of physics you put into the particular problem. So to summarize, what did Chris find when he does these simulations? If he just uses gravity alone, he gets a star formation efficiency that's way too high. It's 47%, way higher than what we observe. If you include just the turbulence of the cloud, it's not enough to support things. You still get way too high a star formation efficiency. When you put in magnetic fields, you're getting better. It's finally when you include all of these different physical effects that you start to approach a number that's down at the few percent level that we actually observe in these clouds. So these are complicated beasts. This is not just a simple molecular cloud, fragments and collapses. There's a lot of physics that goes into trying to understand how these regions actually collapse and form the stars and the solar systems that we have in our Milky Way galaxy today. Now, what about the big picture? What if you step back and look not at the individual clouds, but actually at the whole galaxies themselves? So this is a beautiful Hubble Space Telescope image of the Whirlpool galaxy. You can see the molecular clouds. They're really tracing out these beautiful spiral arm structure in this optical image. And here's what this galaxy looks like in carbon monoxide emission. So here are all the molecular clouds glowing in carbon monoxide in this particular cloud. About 70% of the total luminosity that you see in these clouds exists in these spiral arms, but there actually is a non-negligible fraction of molecular clouds in these inter-arm regions. So all of the star formation doesn't just happen right here where the spiral arms, just the majority of it in these particular kinds of spiral galaxies. Now, one of the really interesting things you can do is you could plot how much CO gas there are in these galaxies versus the star formation rate that we see in these galaxies. And this is a plot that was made by a professor here at the University of Arizona, Rob Kennicott, back in the late 1990s, and it's been revised over more than 20 years since then. So this is sort of the latest version of this particular plot. You have to divide by the area of the galaxies because you want to do a fair comparison. You don't want to just add the total amount because a little tiny galaxy won't have very much total gas, and a great big galaxy might have a lot of gas. So you need to divide by the total area in those galaxies to sort of normalize the measurements so that you compare them. But look what happens. There's this very, very nice, relatively tight relationship. This is a logarithmic scale. So this spans 1, 2, 3, 4, 5, 6, 7. So it's a factor of 10 million in terms of the star formation rate. And down here is a factor of almost 1 million in terms of the amount of CO gas that you have in these galaxies. So if you want to understand galaxies and how stars form, you need to measure this quantity on the x-axis. You need to go make CO observations and see how much molecular gas there is, because how much star formation you have in that galaxy is going to depend directly on how much of the molecular gas that you have in these particular galaxies. Now you might ask, when you look at this plot, here's where the Milky Way is. Holy cow, there are galaxies way up here that have star formation rates that are much higher than the Milky Way. So what are those galaxies? What do those kinds of things look like? Well, here's an optical image of one of them. This is called the Antenna Galaxy. These are two galaxies that are currently colliding. By the way, this is a process that our Milky Way and Andromeda Galaxy are going to go through in about 4.5 billion years. What happens when these two galaxies collide is the gas in these galaxies gets compressed together. You can see that happening here. It forms a whole bunch of molecular clouds and molecular gas that then forms stars. So all this blue stuff that you see here are the very, very young massive stars that have been forming very rapidly. This kind of galaxy, this kind of merger of two galaxies is called a starburst galaxy. And in galaxies like this, you can get rates of star formation that are easily 1,000 times higher than what the Milky Way is forming stars now. And we're going to go through a starburst in about 4.5 billion years. Of course, the sun will be shutting off by then, so there won't be much to worry about unless we've moved off somewhere at that point. Okay, so I just want to finish up with the last couple items, really interesting things that we've learned about these molecular clouds. It turns out that the molecular clouds have a pretty low density. On average, again, I said it's about 100 molecules per cubic centimeter. But within these large, giant molecular clouds, there are dense regions, regions where the density gets much higher, and those are the sites where the stars form. So if you measure that fraction of like what's called the dense gas, so let's say the gas that gets above, I don't know, maybe 10,000 molecules per cubic centimeter, and you plot that down here on this axis, and then you go and look in the infrared and you measure all the protostars that you see in this cloud, you also see a very nice, tight correlation between the number of protostars forming and how much dense gas there is. And these are all the nearby molecular clouds to us that you see here, things like the Pipe Nebula, Taurus that I've been talking about, Orion up here. So you can actually study these particular dense regions within the molecular cloud. So how do you do that? How do you pick out the parts of the molecular cloud that are really dense? The carbon monoxide is a really great tracer, and it sees everything. It sees the low density stuff, it sees the high density stuff, but it's a little hard to pick out, just when you look at the carbon monoxide by itself, what is the low density stuff and what is the high density stuff. So this is where we can use other molecular tracers that can pick out, for instance, just the high density stuff in these molecular clouds. Do you remember this molecule, ammonia? It was the one discovered in 1968. It turns out that it is a great tracer of the high density regions. It only lights up when the density gets above about 1,000 or 10,000 particles per cubic centimeter in these clouds. So this is a project that I did with a graduate student here at the University of Arizona, Youngmin Sal, who's now at the Jet Propulsion Laboratory. And we used, at this time, back in 2013, the first multi-pixel camera to observe at these wavelengths to make these large-scale maps. So on most of the radio telescopes across the world, at these wavelengths that ammonia emits, you only had one detector at the focal plane of the telescope. This particular instrument had 7 detectors, and so we were in hog heaven because we can map very efficiently, and we were able to make this map. This is the size of the full moon here, so you can see this spans a little over 3 degrees, and this is, again, that E E Barnard, very famous central filament that he discovered back in 1907, and now you can see where the dense cores are. These regions right here, these are the future sites of star formation. These are the places where there will be baby solar systems in the next 1,000,000 years or so in these particular regions. Well, it turns out it doesn't stop there with ammonia. After carbon monoxide was discovered in 1970, people started to try to detect all kinds of molecules. And if Bob Wilson had looked at the Orion Nebula today, he might see something that looks more like this in terms of a spectrum. This is a very deep spectrum of the Orion Nebula. Here's, by the way, is carbon monoxide emitting here. Every single little spike that you see here is due to molecules. All kinds of different molecules. Water, sulfur dioxide, okay? Hydrogen sulfide, organic molecules, methanol, quite abundant in there. Things like formaldehyde, acrylonitrile, which is another methylformate. These are relatively complex, at least for interstellar cases, organic molecules you can find in some of these densest regions within the molecular clouds. So this is kind of interesting. The basic building blocks of organic chemistry appear to be in some of these dense regions in the molecular clouds. When we study objects like this is the comet 67P, which we sent a spacecraft to orbit around and actually sniffed the gases coming off this particular comet, we discovered all kinds of things all the way up in complexity to the simplest amino acid, glycine, that was coming off of the gases within this particular comet. It's a natural question to ask, did all this organics form when the solar system formed, or does this get a much earlier start? Did these organics actually start forming even before the stars and the planets started forming out of the molecular gas itself? So the last thing I'm going to show you is this. This is a neat little observation that was done by a current graduate student, Samantha Shibeli. Wave Samantha, she's right over there. So you can ask her about this after the talk tonight. What Samantha did is she went and looked for complex organics, things like acetaldehyde, right here. And here it is detected. And she surveyed that filament that E E Barnard looked at back in 1907, looking at all the dense regions where we found the densest regions where the stars might be forming. And what she found is the complex organics are essentially ubiquitous. They're there. They're in the gas, the dense gas, and the molecular clouds, hundreds of thousands of years even before the stars and planets form in these particular regions. So you have the basic building blocks for organic chemistry and biochemistry right there in the raw gas, hundreds of thousands of years before planets even are forming out of these particular molecular clouds. And I think that's fascinating. We've come so far in 50 years that we can see all these different species. So we've now had 50 years of molecular cloud science since the discovery of the primary tracer of these clouds, carbon monoxide, in April of 1970. And now over 200 molecules have been detected in these molecular cloud regions. And the telescopes that's done the most, the radio telescope on Kitt Peak. Almost a third of all of these detections and discoveries have been made in the intervening 50 years with the telescope on Kitt Peak. So, the next time you go out, and you go out under a dark sky and you look at these molecular clouds, I want you to think about what these things really are. They're the largest structures in our Milky Way galaxy. In some cases, they contain up to 10 million times the mass of the sun, and they are the raw material out of which stars and planets are forming today. And in their densest regions within these clouds, there's a very rich chemistry that it's the basic building blocks of organic chemistry that's already happening in the raw gas that will go into forming stars and planets in the future. Now, before I actually end tonight, I got one little neat thing to show you that we're doing. So I actually happened to have an observing run on the 12-meter radio telescope on Kitt Peak. This is the same facility that did the CO discovery, and we are actually observing as we speak right now. And so I told the operator to go recreate the observation from 1970. So here we are 49 years and 10 months out from the anniversary, and we are observing Orion, the same position, and Tom, it just went away. Darn it. Okay. So, but that's okay because I can put it on my laptop really quickly. No, I think I have to re-log in is what I'll have to do. So if you give me 1 minute here, I think we can plug in, and we should be able to do this off of my screen. Yeah, because of Mac copyrights. Thank you, Apple. Like Bell Labs, they'll get broken up at some point, I'm sure, too. Are we going to do this? So HDMI, it worked earlier when we plugged everything. Oh, hang on, I didn't have it all the way in. Yay, okay, so let me bring over the screen here. There it is. So there's the detection of CO. This is the exact same line, the exact same transition, and we're seeing it tonight, except we're doing this observation so quickly, we have a sensitivity that's many tens of thousand times more sensitive than what Wilson had back in 1970. But here we are actually observing it in real time, and I'll just leave that up for the next few minutes. If I can get my mouse back, I'll bring over the status screen too while we take questions. So thank you very much.
All right, any questions for our speaker? I saw his hand first.
Do we understand the chemistry of how acid aldehyde is actually being created in these clouds?
We think we might. That's the correct answer, I think. And so how this happens is, in these cold regions where it's only about 10 degrees above absolute zero, just from pure gas phase reactions of the constituents of the cloud reacting, it's extremely difficult to build up an abundance of acid aldehyde. So it actually takes those dust grains to help you out. So what happens inside those dusty clouds, when it gets really cold, some of the molecules start to freeze out. So for instance, water will start to form ice layers on the surface of the dust grains. The carbon monoxide, even itself, starts to freeze out and forms CO ice on the dust grains. And what can happen is hydrogen that's in the cloud can react with that ice. It can hit it and it can react. So you can start forming carbon chains, basically organic chains in the ices. And sometimes those chemical reactions have enough energy to pop the molecule back off into the gas phase. And so that's what Samantha's been studying. She's trying to study that mechanism to see if it can actually explain what we're observing. So we're doing a combination of theoretical modeling with actual observations to try to see if we understand the chemistry. There are other aspects of the chemistry of these clouds that we actually understand very well, and we have very good constraints. This happens to be one of the major areas of unknown territory, terra incognita, I would say. So. Yeah.
Does the cloud science give us a better perspective of the total amount of mass? And if so, does that help explain why we keep looking for mass and can't find it?
Right. So it's not enough to explain dark matter in terms of total mass. So if you add up the total amount in all the molecular clouds in the Milky Way, the number is a few billion solar masses total in material in molecular clouds. But if you add up the total weight of the Milky Way, including the halo, all the stars and the dark matter, that number is approaching 1 trillion solar masses. So in terms of the total mass of the entire Milky Way, this molecular component is only about 1/1000th of that. So it can't explain all that missing mass. Okay, it's still not even nearly enough. There's still a lot of it, though. 1 billion solar masses worth of raw material out of which to build stars and planets today. That's still a lot of raw material that the Milky Way can keep making stars and planets for quite a while. Yeah, it does. So if you look at how the gas is distributed in the Milky Way, there's actually more molecular gas interior to us than there is exterior. So if you go towards the galactic center from where the Earth is orbiting around the galactic center, interior to us, there's much more mass than there is in the outer directions of the galaxy. And actually, if you go in It's about 27,000 light years to the galactic center. If you go about half the way there, there's actually what's called a molecular ring. There's a distribution. It's not a perfect donut, a ring. It's kind of broken up and in pieces. But there's a stretch there where the fraction of gas that is molecular is much higher in that particular region. And it probably has something to do with our Milky Way is a barred spiral galaxy. So it probably has something to do with that potential, the gravitational potential of that bar and how gas interacts with it. It kind of gets funneled in, collected, converted to molecular material, and so you get more molecular material at a particular radius in the Milky Way.
Is there a limit to how large a molecular cloud could get before it collapses?
Yeah, that's a good question. So yes, there is. There's a typical length associated with the process of fragmentation in physics. It's called, the fancy name for it is the Jeans length, right? And so once you get above a certain size, you will naturally want to fragment and form smaller objects. It's a little bit of semantics as to what you call the size of the molecular cloud, because some of these molecular clouds are kind of almost connected to each other. And so there's places in our Milky Way galaxy where we can't get above the plane of the galaxy and look back down. But if you could and could look at the spiral arm structures, there's like whole chains of molecular clouds. And some of those, they span over 1,000 light years easily, right, as they curve around in the spiral arm, all connected chains of molecular clouds. And so how you exactly divvy those up is almost a little bit of semantics in terms of the length. So it's a bit of a hard question to answer because of that semantics part of it. But yes, there is sort of a typical size. We can't get much bigger than a few hundred parsecs for these things.
Question here.
I noticed some of your waveforms with various spectral lines look remarkably like a radar.
Like radar? Yeah, so they like spike out. It's a really narrow range of frequencies.
And they're exactly frequency coherent between these?
That's right. So this has to do...
I guess you're modulating a radar there.
Well, those frequencies are very well spaced for these molecules. This has to do with quantum mechanics. When you solve Schrodinger's equation for the structure of the molecule, there's a very specific equation that tells you how the energy levels should be spaced. And they're very regularly spaced for a lot of these molecules. That's why you see these very regular patterns. And not only that, the frequencies at which the light come out, it's a very narrow range. And so that's why it's such a really narrow spike that looks like a burst that you would send out that's a very narrow frequency burst for radar, right? Yeah.
Sir, I've heard mentioned in science and astronomy lectures the precursors of life, over and over again. Is there any evidence in either in space or in a lab of life actually being created?
Not to my knowledge. So that's the simple answer to that particular question. Like from basic constituents, the types of experiments have made the basic biochemicals that life needs to exist, right? And those have been made under laboratory conditions, and we think they're forming in these regions where stars and planets are forming. So that basic raw material is there. But whether or not you can get it to be self-replicating, first through some sort of chemical evolution that then turns into biological evolution, it still is a mystery as to exactly how that happens, and nobody's ever been able to replicate that.
Yes, sir. So that between us and Orion, there's this huge molecular cloud, but I guess it's somewhere between us and it's spread out, right?
Yes.
Is it possible that there's maybe just a large chunk that's blocking Betelgeuse that's making it look the way it is?
That's actually one of the hypotheses for what's happening to Betelgeuse right now. So Betelgeuse is a red supergiant star. It's probably just started burning helium in its core. So it's in the last phases, and it's got less than 1 million years, probably just a few 100,000 years to go. And it is massive enough that Betelgeuse will go supernova. But those kinds of stars, they are like a little bit like a lava lamp. They're highly convective. The gas is just churning up and down, and they're heating up and cooling off. And occasionally, these stars, they all have pulsational modes that the atmosphere is kind of pulsating in and out. And if you look over time, Betelgeuse has had historical variations. It's lower than it's been since photometric measurements have made, but it's probably not lower than it's ever been in the last several thousand years. This might just be a series of periods that are adding up, that are basically, we just happen to be at a minimum where everything's kind of in phase, and it's a whole bunch of minima adding up to make it as deep as it is. But the other hypothesis is that Betelgeuse is slowly blowing material off of it. It's shedding material off of its outer atmosphere, and maybe we've just got a colder blob that's got a bit of dust in it that has come off the surface, the photosphere of Betelgeuse, and it just happens to be blocking us right now, and that's why things may be a little dimmer. So there's ways to test that, actually, by looking at what Betelgeuse is going to do over the next 6 months. If it's just a combination of periods, you expect it to go up at some point. But if it's the dusty cloud, it might stay low for a longer period of time. So you have ways of potentially testing those different hypotheses. Yeah.
Is water, all of our water, created in molecular clouds?
No, I think it's formed, some of it is also formed during processes when the solar system forms. So not 100% of it can all be, every water molecule can't be traced right back to the molecular cloud. It may have been dissociated and then reformed at some point later in the stage. But what I can tell you is that all regions that are forming stars today in the Milky Way galaxy have copious amounts of gaseous water in them because we can observe those signatures. Many, many, many times the Earth's amount of water is available in these forming solar systems. Matter of fact, the Earth is actually kind of dry, even in solar system context. I mean, there's bodies in our solar system that have more water than the Earth does. The moon Europa of Jupiter has a subsurface ocean underneath its ice cap that has 2 to 3 times the amount of water that's in our Earth's oceans. And there's other bodies in the outer solar system that also have large reservoirs of water, even liquid water, like Enceladus, right, in those other bodies in the solar system. In forming solar systems, water is one of the abundant molecules. It's easily available. And the water that came to Earth probably got delivered. So some of the water that was originally on the Earth may have gone away, got destroyed, evaporated, and then was later brought in by meteorite impacts, asteroids, and comets that brought in and redelivered what we have as today's Earth's water.
Okay, I'd like to remind you that our next lecture is 2 weeks from tonight, March the 2nd. Dr. Katie Greer will tell us about supermassive black holes and other galaxies. Hope to see you then. The telescope is open for your viewing pleasure. I'll stamp student assignments down here. Let's thank Professor Shirley one more time.